Okay, morning. Let's continue the discussion about Thv and Norton analysis, Thv and Norton theorems. And let's bring up the class notebook. All right, so we stopped here where I introduced the topic of Thv and Norton theorems. The basic essence of both is that if you have a large linear circuit comprising of multiple sources, whether it's a voltage source, current source, and doesn't matter how many sources you have, you can represent that entire circuit as one single voltage source or one single current source. The voltage source would have a resistor in series, and the current source would have a resistor in parallel. That resistance is known as the Thevenin resistance. That's the same for both equivalent circuits. The voltage source is named after Thevenin, so it's known as the Thevenin voltage, and the current is named after Norton, hence Norton current, IN. So you have voltage, resistance, and current. What equation do you think relates the three? Ohm's law. VTH can be given by the product of IN and RTH. Okay, RTH. So Thevenin resistance times the Norton current gives you the Thevenin voltage. So if we are trying to determine the Thevenin equivalent circuit for any larger circuit, we can find any of the two quantities and then determine the third. Okay. But there are often times where we cannot find the resistance directly. RTH cannot be determined directly. Some circuits. Some circuits. And hence we would use the same expression. IN. Okay. And this is the reason why students need to know how to determine each one of those three quantities. Okay. You have to be able to determine RTH, Thevenin voltage, and Norton current independently. Well, the good news is, again, this is not something new. This is something that we already learned in chapters 1 and 2. Okay, again, as I stated earlier at the beginning of this topic, this is not a new analysis technique. It is a theorem. It is the application of all the techniques that we have learned so far. So let's summarize, see how we are going to actually determine the Thevenin voltage, Thevenin resistance, and the Norton current. The first thing, the absolute first thing to do is to establish your terminals of analysis. Okay, so you establish your terminals of analysis. Now, if the question states, determine the Thevenin circuit between terminals A and B, then you begin your analysis as it is. No need to do anything. However, if the question states, determine the Thevenin and Norton equivalent circuit as seen by a particular component, then we remove that component from the circuit, and the open terminals left behind are the terminals of analysis. As an example, in the previous example that I stated here, I said we are trying to find the value for R6. So we remove R6 from analysis and we analyze the rest of the circuit between these two terminals, out plus and out minus. R6 is not part of the analysis. Does that make sense? An analogy can be made. Let's say if there were 30 students in the classroom. If someone were to ask if I am instructing 30 students in a classroom, someone outside from the classroom could say there are 31 people in the room. But if someone was to ask me, how many people do I see? Then the answer would be 30, not 31. I have to remove myself from the analysis. I have to remove myself from the count. Does that make sense? So if the question states, determine the Thevenin or Norton circuit as seen by a particular component, then that component is no longer part of your analysis. You remove it, and then you analyze the rest of the circuit between those open terminals. Let's take a pause. Let me know if you have any questions. Any questions? Okay. As seen by can also be stated as load or follow-on circuit. As seen by can also be stated as load or the follow-on circuit. And I'll give you a real-life example. If you if we take any audio video receiver, that audio video receiver is made up of 3 different parts, or not 3 different parts, actually 2 different parts, which is then connected to a speaker. It's a preamp and an amplifier. This preamp will have a source. That source could be anything. Could be your gaming system. Could be your Blu-ray player, Blu-ray DVD player. Or anything else for that matter. Now, this would go to a speaker. Right there. So the source could be any electronic device, goes into the preamp. The preamp will strengthen the signal, impart in a little bit more current and voltage, and then drive it to the amplifier section. The amplifier section will in turn take that, amplify the power and the voltage and the current, and send it out to the speaker. Now, every single stage, there has to be impedance matching or resistance matching. And so the preamplifier, the output of the preamplifier has to be matched to the input of the amplifier. Okay, and that is known as impedance matching. So the Thevenin resistance of both should be the same. And the same thing applies here also. If you look at the output of any amplifier system, it'll always tell you that it can drive, like, say, 100 watts into an 8-ohm speaker. Your speakers, if you're buying them separately, the speakers will have an impedance. It basically tells you the impedance or the resistance of the coil of the speaker, which is typically around 8 ohms. So speakers in real life have 8 ohm or 4 ohm impedances or resistances. Okay, so the output of the amplifier is matched to the particular speaker. Now, this is of course the real life. Coming back to our theory, the way we determine the Thevenin resistance, and I'll go to the next page and I'll come back to the first one. The way we determine Thevenin resistance is basically we find Req. We find Req. The Req of the circuit, Req of the circuit as seen from the open terminals. Open terminals. Okay, Req as seen from the open terminals, that gives you the Thevenin resistance. And what do we do for that? Well, we reduce all independent sources to 0. And reducing all independent sources to 0 means replacing all voltage sources and all current sources with a short or a open circuit. This is something we did for application of the superposition principle. So let's take a 10-second pause, think over it. Let me know if you have any questions. Okay, any questions from anyone? Okay, so as I was saying, to find Thevenin resistance, you replace all independent sources in the circuit to 0. This is something we did for superposition. Okay. Then for Thevenin voltage, the modification we make is basically we analyze the open terminals, and from those open terminals, we simply apply any technique we want: node voltage analysis, mesh current analysis, or superposition, Ohm's law, KVL, KCL, whatever technique you can think of to determine the voltage between the open terminals. Okay, the open terminals. So this would be open circuit voltage, and this open circuit voltage is VTH. So your Thevenin voltage is the voltage you would measure between the open terminals of analysis. And then for Norton current, all we do is we take, we take the open terminals and we place a short circuit wire between those terminals, and that the current flowing through those terminals will give us the Norton current. So that short circuit current is known as ISC, and ISC gives us IN. Okay, VTH and IN. All right, let's take a pause. Let me know if you have any questions. Any questions from anyone? Okay. All right, so now let's go back here. So we have the 3 quantities, right? 3 quantities. We need to redraw the circuit 3 times for analysis. Once for Thevenin voltage, once for the current, and once for the resistance. And all three circuits are different. So we have to analyze each circuit independently of the other two. Okay, the circuit that you use to determine the Thevenin voltage is different from the circuit for Norton current. It's different from the circuit for resistance. For resistance, there are no sources present in the circuit. Okay, so again, this is a very important point. You have to redraw the original circuit 3 times, once for voltage, once for current, one for resistance. All three circuits are different. They have no bearing whatsoever on the other two. Okay. And then, of course, you can use any technique, any method you want. Okay. Are we ready for an example? All right. So the question, the problem statement here is determine the Thevenin equivalent resistance between terminals A and B. Thevenin equivalent resistance between terminals A and B. It's not asking for anything else. Now, A and B, it does not state determine the Thevenin resistance as seen by a particular component. So in this case, we don't have to do anything. We directly analyze between A and B without any modification. The first step for Thevenin resistance is to reduce all independent sources to 0. So I will first draw out the resistors, and then I will draw out the sources, or at least the place where the sources are connected. And let's see, that's A. And that's B. This is R4. Okay, so we have V1, V2, and V3, 3 voltage sources, and we have to reduce them to 0. So we remove the voltage source and place a wire in its place. And the same thing here. And then the current source, of course, you don't have to draw anything out. This is where the current source was connected, so we may as well not draw anything. Right, the current source is removed. This was the place where I1 was connected. This is R1, R2, R3. And our job is to find REQ between A and B. But before we do that, let's take a 10-second pause. You think on the setup, and let me know if you have any questions. Any questions at all? Does the procedure make sense? So if I wanted to find REQ, I start at the farthest end. Let's say R1 is parallel to R2. That is in series with R3. And the entire combination is in parallel with R4. That is the answer to REQ. and my RTH Thevenin resistance is equal to Req. And that's it. That's the answer. Let's take a pause while you write it down. Let me know if you have any questions. Any questions at all? Okay, if there are no questions, then let's take a break. We take a 5-minute break and meet back at, let's see, it's 10:56, 11:01. Let's say 11:01.